Hello, my name is Joe Zhong, and I am a PhD candidate from VI Lab KAIST. And today, I will give a presentation on our paper named Multi-Agent Long-Term 3D Human Pose Forecasting via Interaction-Aware Trajectory Conditioning. First of all, let's look at what human pose forecasting is. Human pose forecasting is a task of predicting future sequence of human motion from past human motion. The motion is represented by any number of joints, and in our case we use 15 joints, which are represented in 3D space. Human pose forecasting can be used for embedded systems such as mobile robots or autonomous vehicles, and for VR/AR applications. Our work tackles human pose forecasting in complex scenes. Indeed, previous SOTAs struggle on complex scenes with three or more agents and 2 or more seconds of forecast horizon. Therefore, in a method perspective, we propose a coarse-to-fine method where global trajectory represents the coarse intentions and local pose represents fine intentions. This coarse-to-fine approach efficiently models the complex and multimodal nature of human interaction and motion. We also consider a dataset perspective on human pose forecasting. Previous datasets do not include complex interaction in a real-world environment. Therefore, we parse a new dataset that includes complex multi-agent interaction with up to 24 agents in a given scene. Let's dive deeper into the methodology. The crux of our work is modeling human motion in a coarse-to-fine method. The global trajectory is used to model the coarse intentions and their coarse intention in locomotion. Then, the local motion, which is considered as fine intention, is forecasted with conditioning on the global trajectory. When forecasting global trajectory, we consider both past global motion and past local motion. Interaction between agents is computed based on both trajectory embeddings and pose embeddings. Compared to previous works, our attention mechanism models interaction based on the dimensions of coarse intentions. And therefore, our method only scales based on the number of agents. In doing so, our method is able to handle complex scenes with 20 or more agents. Here, we explain the dataset parsing framework in detail. We parse the JRDB dataset, which captures human motion via a mobile robot in a campus scene. The robot uses RGB, LiDAR, and many more sensors. We mainly use RGB image and 2D pose annotation and 3D bounding box annotation to parse the dataset. From RGB image, we extract initial 3D pose using an off-the-shelf SOTA algorithm. Then, we refine the 3D pose using 2D pose and 3D bounding box annotations. And then we get the final refined 3D pose. Please refer to the paper for more details. Here is an example of the parsed dataset. As seen on the bottom video, the dataset includes some diverse motion, such as tying shoe. Our method surpasses previous SOTA methods on all global, local, and joint motion metrics. We evaluate on 3 datasets. CMU mocap and 3D-PW datasets are captured with IMU sensors, and JRDB GMP is our parsed dataset from RGB image and 2D, 3D annotations. We surpass previous SOTA algorithms on all datasets. Compared to previous works, our method forecasts a more natural walking motion, while previous works show some feet skating. On the JRDB GMP dataset, our method shows 2-person walking side by side, while other works end up in collisions. Here's a comparison in a video format. Previous works all show a natural drifting motion, while our work forecasts a natural walking motion. Even for motion with minimal global displacement, our work forecasts a more realistic and dynamic motion. As seen in the video, our work forecasts a more dynamic punching motion, while previous works remain mostly static. If you have any questions or comments, please feel to contact us. Thank you for watching our presentation, and please find us in the conference.